Okay, welcome. My neighbors are being loud, and I don't know why. I like quiet neighbors, cottagers up here. Okay, uh, so what we're gonna do is we're actually gonna get into some more algebraic-y, interesting stuff. So we're gonna start talking about vector definitions of points, lines, and planes. Now, I could say in three space, but really, you're not going to do planes in three space otherwise. With vectors, I guess, is what I should stipulate here. With vectors. Wow, they're being really loud, annoying people. Okay, so on we go. So let's cast our mind back, and let's think about the equation of a line in R2 and think about how we've classically done that. So if we think about grade 9, well, that was a long time ago for a lot of you. Grade 9, we had y equals mx plus b. Okay. And at the time that seemed mind-boggling. So let's look at an example and see kind of start trying to extend our understanding of that into the type of understanding we have now. So imagine that we had how about y equals, I don't know, like if I said 4/7 x plus 1, right? So I'm going to go ahead and I'm going to just sketch that. So we would go up to a y-intercept of 1, and then we would have a rise of 1, 2, 3, 4, and a run of 1, 2, 3, 4, 5, 6, 7. And so we'd have another point out here, and then our line would go through that, right? So like this, there's our line. Okay, so we've got a run of 7 and a rise of 4, and it goes through this point right here, and that point is the y-intercept of 1, but we could list as an ordered pair, and the ordered pair would be 0, 1. So that's classically how we've always done that, but imagine that we wanted to talk about a vector definition of this. Here's how we could do this with a vector. Imagine that we said, all right, we've got this, it's got to go through this point here. So we've got a point on the line, and the point is equal to 0, 1. So we know that point lays on the line. It's not the only point on the line. Clearly, it's a line. There are an infinite number of points on that line. And then the slope, classically, has told us, where we're going. So the slope in this case is rise over run, so 4/7, right? So that's the slope. But slope is really, it's telling us the direction, right? So slope sort of tells us the direction. So let's consider how we could use that to our advantage. Imagine that what we were doing is we actually wanted to make this a vector. So we could say, I've got a vector that goes along here. And what would if I took that vector and made it from the origin, what would that vector be? Well, that vector in this case would actually be this vector right here. So if I call that, what I'm going to call that our direction vector. This direction vector tells us the direction. So the direction vector has the coordinates 7, 4, right? So the direction vector is 7, 4. Now, direction vector 7, 4, if I just list it as an ordered pair, you're like, that's not where that vector would be. And it's kind of like, if we made this the vector OD and said, oh, it's 7, 4, what would it be? Well, it would be the, collinear, and it'd be the same length, and it would be just sitting down here. It would still go out the same distance. This vector right here would be OD. But the direction vector 7, 4 says, I want you to walk along X axis 7 and then walk along the Y axis 4 from this starting point, and it's going to get you to another point on the line, and it's going to get you to another point on the line. Now, that would find us a series of points that are equidistant apart, right? It would be there, and then that's probably too close, but nevertheless, there. And so that's going to define a whole bunch of collinear points. It doesn't actually fully describe the line. And so here comes our vector definition of an R2 line. So vector definition of an R2 line. That shouldn't really go through those. It should be underneath that. So the vector definition of an R2 line. The nomenclature for this is a little bit weird. So we're going to say that P, and I'm going to talk about that in a second, is equal to P naught plus T times vector D, where T is a member of the reals. So, that doesn't strike us as anywhere near as nice as what we used to do up here. However, P represents any, alternatively, every point on the line. And P naught is a point on the line. So this is an actual point on the line, right? It's an actual point. Looks like actual point on the line. D is our direction vector, and T is the parameter, which is a member of the reals. So what this actually does, this is actually pretty cool. And I've kind of lied to you, but it's a good lie. And we'll come back to it in a bit why it's a lie. But for now, you can think about a vector equation of a line by saying, get out to some point on the line. Now, P naught, in this case, the obvious choice would be 0, 1. But it could be anything, right? Like the next point out here that's easy to get to is to advance 7 and go up 1. So that point right there would be 7, 5. So our P naught could just as easily be 7, 5 as 0, 1. Or we could go out another one. So we could do like 14 and 9, right? 14 and 9. Or we could go backwards and we could say, -7 and -3 out here, if I've done that correctly in my head. -7 and -3. Any one of those could equally be a point on the line, any point that's actually on the line. And so if I'm out on the line, so I drop Curtis on the line somewhere and I say, Curtis, you are allowed to simply follow this direction vector as many times as you want, and it doesn't even have to be an integer multiple times, right? It could be 0.1 times, it could be -17 times. So this direction vector says, once you're out on this line, you follow this heading either forwards or backwards, and you are still going to be on the line. So you can imagine that if I multiply that by any and every number in the real number system, it is going to take us to every one of the points on the line. So this defines the equation of this line in 2 space. So I think about this as, so I'm going to grab some other colors here. And I'm going to talk about why this is sort of a lie, but it's a really good lie. So I consider this an anchor point. Okay, it's an anchor point because it anchors me onto this line, and it can be any point on the line. It is an anchor point. It gets me out to the line. And then the direction vector tells me how far I'm allowed to, or the direction I'm allowed to move after I've gotten out to the line, right? So this right here, this guy here, this is, my movement direction. So the movement direction says you can follow, 7/4 as many times as you can do 1/10 of 7/4. So we could be like, 0.7 and 0.4 up, so 0.7 and 1.4. Or it could be 100 times that. So it could be 700 and 401 would be another point that's on the line. So this P represents, alternatively, every point that exists on the line. And this is how we get to it. We go out to our anchor point, and then we follow this direction vector. So that's how I absolutely always 100% think about how this works. Here's why it's a lie, but it doesn't really matter. This cannot be a point. And you're like, what? Because you can't add a point and a vector, right? You have to add a vector and a vector. So because of that, this really isn't a point. It is really a vector that is O P naught. And so, if I use the point 0.75, P naught would actually be O P naught, and it would take me out to there. So really, this isn't an anchor point. In actuality, it is always going to be an O P naught. It's actually a vector that gets us out to the line because you can't add a point and a vector. Now, I never, ever, ever think about it like that other than when I'm teaching it. I totally think of this as being a point on the line that I then can add a direction vector to go from there. And, it works. But the true definition is you can only add a vector to a vector. So that's why it's actually OP naught, not just P naught. Okay, so I'm going to define it like this, and I'm going to use that as a definition again in R3 as well. But know that when I say an anchor point, it really is the vector that takes us from the origin out to that point. So it's really OP naught, but I'm just going to reference it as P naught as the point that is on the line somewhere. Okay, so that's pretty cool. So alternatively, that's there's the vector definition of a line in R2. Let's right over here. So P is equal to P naught plus T times direction vector D, where T is a member of the reals. That's one way we write it. It can also be written as PXY, right? So this is all of the possible points of the line, is equal to P naught, which is X naught, Y naught. Again, this is my anchor point, or the direction vector that gets, or the vector that takes us out to that point, plus T times the direction vector. And I just usually leave it as that. But I mean, if you wanted to make it X sub D and Y sub D, you could do that as well. But I just think about it as the direction vector. Okay, so lovely. So again, this is all points on the line. That's not all. All points on the line. On the line. This is the anchor point. And this is, of course, the direction vector. Okay, lovely. Awesome. Now, on we go. So, do I want to do that? Okay, so that is the vector definition of a line. So carefully, that's actually the vector format or definition. There it is right there. It's not the only form. There is another form. So P naught, sometimes it's also just written as X comma Y, again being representative of every point on the line, is equal to X naught, Y naught, my anchor point, plus T times D1, D2, where T is a member of the reals, and the direction vector is equal to D1, D2, right? Now, these are all three of these things. I don't have a highlighter that I can use, but I'll just underline them with, whatever color that is. These are all simultaneously the vector format of a line. So it's known as the vector form of a linear equation. So, vector form of a linear equation. But they can be in different forms. So let's move on and examine a different form. So there's another form called the parametric form of a linear equation. So the parametric form of a linear equation is actually pretty cool. It is x equals x naught plus t d1. And so what I've done there is I've just picked off the x coordinate of all of those pieces. And then we're going to have a similar equation that's y equals y naught plus t d2. Okay. And so again, here still is t is a member of the reals. So this is called the parametric form of a linear equation because it involves this thing here. This is the parameter, right? So that is the parameter, hence the name parametric. That's the parameter. So let's look at how we can use that. So imagine, given the following, so let's look at some examples here. That's not the only forms, but we're going to start with this. So imagine given, how about we're given y equals negative 3/4 x plus 8. I would like you to determine the vector and parametric forms of this equation. Now, I always, when I'm doing this, will start with a diagram. Always. Always, 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 always. So it's not horizontal, but close enough. So I got this point up here that's 8, and then it's got a rise of 3 downwards and over 4. So, there's negative 3 and there's 4. And so there, the line goes like this, like that. Okay. Now, what's interesting is I will then always, even on my own, draw in. I should do a thicker line, maybe. Can I do it like that? I think I can. Let's do it. There we go. Go back to being thinner again. Brush size, fine. So this vector here, oh, it's still thicker than I want. Stop that. Oh, no, 2, 3. There we go. This is the direction vector. And so I want to figure out what the direction vector is. So direction vectors always go x, comma, y. And so in this case, the x I went across 4, the y I went down 3. So there's my direction vector. Okay. And we're going to talk about I'm sure that you can figure out exactly how to turn a slope into a direction vector. But I personally always just solve for it on the fly like that. So there's my direction vector. So if I want the vector form, the vector form needs to look like P is equal to P naught plus T times a direction vector, right? So P naught can be any point on the line. So 0, 8 is a lovely and obvious choice, but it's not the only choice. I could also do, it's over 4, so 4, comma, and it went down 3. So this is really 4, comma, 5, right? So 4, comma 5. So I could use either 0, 8 or 4, comma 5, or I could go and find another one. How about 8 and 2 would also be on the line, or negative 4 and 11 would also be on the line. All of those would be acceptable. Okay. When it came to marking the tests for this, I had a student, my good friend Carson Wood, would go and find the most ridiculous other points that were on the line. So when it came for me to mark it, I'd have to spend quite a while doing calculations to see whether in fact his anchor point was on the line. He reveled in making me do more work. Jerk. Actually, I think he's a great kid. Okay, so I'm going to just use 0, 8 just because it's nice, plus T times the direction vector, and we've said the direction vector is 4, -3. Now, just as easily, we could have done the direction vector that went in the opposite direction, right? And so we could have done -4 and +3 because they are collinear. They go in the same direction as one another. But there is a convention that when we have a direction vector, the x-coordinate should always be positive. So we always want for a direction vector, only a direction vector, always positive for the direction vector. Okay, the x-coordinate, right? The y-coordinate and the z-coordinate, when we get into R3, there's no necessity in that regard. Okay, so there is the vector form, or one vector form of that line. How many different vector forms are there? There are an infinite number of different vector forms, right? You know, that's just how it is because you could choose whatever anchor point you wanted. Now, not only should a direction vector always be, I should have probably written that was positive, always positive for the direction vector. And not only that, it should also be in lowest terms, right? So this direction vector just tells us how we want to go. 8, -6 would work just as well, but we always want to reduce the direction vector. Now here's where we have to be really careful. Direction vectors can and should be reduced, and the x-coordinate should always be positive. That is not true of the anchor point. If this anchor point was 2, 8, so it's not. But imagine, hypothetically, imagine that we had a P naught that was 2, 8. You might think, oh, I can reduce that to 1, 4. No, you can't. This is a location, right? That changes the location. This is a direction. So if one was 4, 3, there it is right there, 8, 6 is describing the same direction, right? 40, 30 is describing the same direction. So we can change the magnitude of this by putting it into lowest terms. And in fact, we should. However, anchor points, bad. We're not going to because that is changing locations. Changing lengths, okay. Changing locations, not okay. Okay. Gross. I'm just sorry. I have a touchscreen laptop and I just killed a bug, and I can't drag it like that. I suck. So on we go. Right. So there is the vector form. We got that. That is one of the vector forms. Lovely, lovely, lovely. So there's a vector form. I also want the parametric form. Well, the parametric form is going to be x equals 0 plus 4t and y equals 8 minus 3t. Right? So you can see at a glance that this forms our P naught, and similarly, this, without the t there, forms our direction vector, right? So we can go between those forms pretty easily. So how can we use this? So imagine that I said, given this line here, or let's take another example here. So let's look at another example. Given the line, how about if we did, I'll give you a vector form. Xy is equal to 7, 1 plus t times, I don't know, 3, -2. 3, -2. So there's a line. I want you to do a few things. I would like you to find. Oh, my cat just shut the door. That was lovely. Find the. So that's the. I would also like, I guess, the parametric form. That's one thing I want you to do. And the second one, and that's trivial. You should be able to do that really easily. Is I would like to know, is the point How about 37, negative 21 on the line? Okay, so parametric form, dead easy, right? So number one, we're just going to say x is equal to 7 plus 3t, and y is equal to 1 minus 2t. Again, there's my p naught, 7, 1, and my direction, 3, negative 2. Easy, 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 easy. So that's easy. There's number one. Number two, we want to know if this point is on the line. So here's where, the parametric form kind of comes into its own. That's a parameter. This t must be consistent for any single point, right? So the t can be any value you want, but that value is going to take you to different points. For any one point that's on the line, that t has to be the same. So what we can do is we can say, oh, this is an x coordinate and this is a y coordinate. So I can set up two equations here. We know 37x is equal to 7 plus 3t. And we have a secondary equation, so that's using the x coordinate. And if we use the y coordinate, we're going to have negative 21 is equal to 1 minus 2t. And what I can do is it's only one or like there's two equations, but there's only one unknown, right? So we can take and we can solve here. So I'm going to move that over, and we're going to get that that's 30 is equal to 3t. Divide both sides by 3, divide by 3, and we're going to find out that t is equal to 10. So we've got one solution that says t is equal to 10. We can do the same thing over here. We're going to move this over, and we're going to find that that's negative 22 is equal to negative 2t. Divide by negative 2, divide by negative 2, and we found out here that t is equal to 11, which means that it is inconsistent. Okay, so if it's inconsistent, therefore, the point, whatever it was, 37, negative 21, is not on the line. Get out of the way, you. I do, no, not like that. Ooh, 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 what's going on? Okay, so that's not on the line. Okay, pretty cool. Now, if these match, of course, what that would demonstrate is that they are on the line. Okay, easy the peasy. On we go. So there is another form of a line. So if we take and I'm running out of space. I think maybe I'm going to stop this right now, and then I'm going to post a second video in a moment after I have set this all up. Okay, great.